Welcome everyone to my talk about implementing the visitor pattern in a simpler way using pattern matching, records, and sealed classes. My name is Haim Michael. I live in Tel Aviv and I'm a father for 2 kids. I'm into programming for more than 40 years. My passion lies with teaching and endless learning. I continuously learn and evolve. I focus on teaching advanced topics in software development, both in academic institutions and IT companies. You can find my online courses at Udemy. You can also find my online courses in Hebrew at Haim Michael Pro. And you can find more information about the training services I deliver for software developers at lifemichael.com. I'm into Java for 30 years, a bit more. But I'm also into many other programming languages, especially those that are on top of the Java virtual machine, such as Scala and Kotlin. So, the use of record classes combined with sealed classes and pattern matching can make it simpler when implementing the visitor design pattern. So our talk will start with describing the problem the visitor design pattern provides a solution for. Then we shall go over the traditional implementation, the way we used to implement a visitor before the emergence of pattern matching, sealed classes, and records. Then we shall go over the modern implementation that is now possible thanks to the use of pattern matching, visitor, and sealed classes. And we will conclude with going over the benefits of using records, sealed classes, and pattern matching when implementing the visitor classic design pattern. Let's start with describing the programming problem for which the visitor design pattern was created. Well, in many object-oriented systems, we have a class hierarchy that we want to traverse the objects instantiated from those classes, or to perform a specific operation on each one of the objects, such as evaluating each one of the objects or print a detailed information about each one of the objects. Well, in some cases, it makes sense to add those new operations directly to the classes we have in that hierarchy, but in some cases we can't for some reason, or we don't want because we don't want to clutter the new code with unrelated logic. Maybe we follow the single responsibility principle. Maybe we want the logic to be somewhere else because it's not a simple logic to be added directly to the classes. Maybe we can't change the source code of the classes. Maybe the system already exists and now we want to add new operations, but we don't want to introduce changes, or we can't introduce changes in those classes. So the visitor classic design patterns aims at solving the following problem. How can we define new operations on a set of related object types, example, binary tree nodes, shapes, expressions, and so on, without modifying their source code, without duplicating logic across types? How can we achieve that? Or if you want the text by the gang of 4, how to represent an operation to be performed on the elements of an object structure. Visitor let you define a new operation without changing the classes of the elements on which it operates. So for that specific programming problem, we have the visitor design pattern. The visitor design pattern, when you implement, actually decouples the operations from the object structure. The operations will be in a separated location, a separate class, allowing us to define new operations without changing the element classes, without changing the classes from which the objects in that binary tree or graph of objects, or just a simple linked list or an array, were created. Let's see the traditional way of implementing visitor, the way we implemented visitor before pattern matching, sealed classes, and records were added to the Java programming language. In order to implement visitor at that time, we had to define a class that, when instantiated, the object we got will be used as a visitor that visits each one of the objects we have in our linked list, an array, or binary tree, or whatever data structure you can think about. Now, in order to have the visitor object visit each one of those objects, we had to implement accept, so that it would be possible to invoke accept on each one of the objects, so that whenever accept is invoked, a visitor is passed over, and then within the accept, the visit method was called on the visitor object in order to perform the operation. Now, in order for that to work, we had to define multiple versions of visit for each one of the possible types. So you can imagine the interface expression and then various classes that implement expression directly or indirectly, and you can imagine that the accept method that was defined in expression as an abstract method was eventually implemented for each one of those classes that implements expression, so it would be possible to call accept on each one of those objects that were instantiated from those classes that implement expression. Now, whenever accept is invoked on an object which is actually an expression, because it is an object that was instantiated from one of those classes that implements expression, that accept method that was invoked took as an argument the reference to the object that is served as, that is being used as the visitor. So that inside the accept method, visit was invoked on the visitor object. Now, the implementation of visit is the new operation that we want to have available for all of those objects we have in our linked list or array or whatever data structure you can think about. So, because we have different implementation for visit for each one of those types that implement expression, we had to define those variations of visit as abstract method in the interface visitor, and then implement those methods in the class that implements visitor. Then, on the other end, in each one of those classes that implements expression, we have the accept method, so that it would be possible to invoke accept on each one of the expression objects. So here, for instance, the implementation of visitor, and as you can see, we have a separated implementations for each one of those versions of visit. Now, let's take a look at the code itself in the IDE. So we have the interface visitor, and then a class that implements it. Then on the other end, we have the interface expression and various classes that implements expression. Difference, multiplication, number is the simplest option, total. So eventually, when having, for instance, an array of objects that are actually expressions, meaning each one of these objects was instantiated from a class that implements expression, we can go over those objects and call the accept method on each one of them. And then whenever accept is invoked, the reference to the visitor object is passed over. Inside the implementation of accept, we will find the call to the visit method. This will be passed over. Now, if you go back, this is the interface. The implementation, as you can see, of that interface in each one of the classes that implements that interface include the implementation of accept. And the implementation of accept always includes a call to visit on the visitor object, passing over this. Now, because we have overloading for the visit method, we have different versions for each one of the possible types. the correct visit will be invoked in accordance with the object on which accept was called. So eventually, when looking at this code, you can see that we go over all of those objects, the array alt. On each one of them, we call accept, passing over the visitor. Inside the accept method, we shall see a call to the visit method on the visitor object. This will be passed over as an argument. So this is how the traditional way we used to implement visitor. Now let's see how can we easily implement visitor by using record classes, sealed classes, and pattern matching. We will start by defining the interface expression and then multiple classes that implement expression, either directly or indirectly. Then we will define a method that can take an expression object and perform the correct operation for that specific object according to its type. So first we define the interface expression, and then we define those classes that implement expression. We will use the record keyword in order to get classes that automatically include various methods such as equals, toString, and so on. Now take a look at the evaluate method. This method, when invoked on an evaluator object, expect to get an expression object. Now it can be a reference for an object that was instantiated from one of those classes that implement expression. And then using a switch expression, the correct evaluation will take place. So for instance, if evaluate took an object, which is actually an object that was instantiated from the type number, then we can use pattern matching in order to extract the value that specific number object holds, and that will be the value evaluate returns. If the expression object that evaluate took is actually of the type total, then we can use pattern matching in order to extract those two expression objects that the total object is composed of, and then evaluate each one of them separately. So for instance, we can expect an expression of the type total that is actually a composition of two separated expression objects. Each one of them can be of any of those types that implements expression. Now, if you look at this code, you can see that the interface expression was defined as a sealed type, meaning only the specific types listed here, number, total, difference, and multiplication, can actually be part of our program. That leads to having a switch expression that can always work and can always evaluate the expression object according to its type. Now you can imagine a program that includes multiple expression objects and then calling evaluate on each one of them, one after the other. Or it can be one expression object, in this case an object of the type multiplication, that includes two expressions. In this case, each one of them is of the type total, and so on. So it can actually be evaluation that takes place using recursion. Let's take a look at the code in our IDE. So first we have the interface expression. As you can see, it was defined as a sealed type, meaning only number, total, difference, and multiplication are the types that are allowed to implement expression. So each one of these types, difference, evaluator, not evaluator, difference, multiplication, number, total, each one of them, as you can see, in this case, is a simple type that was defined using record. difference, multiplication, total, number, and that's fine, because the evaluation of each object that was instantiated from one of these classes takes place using the evaluator class. Evaluator class as the method evaluate. So we can call evaluate on an evaluator object, and whenever evaluate is invoked, it takes an expression object, and the evaluation takes place over here. According to the type, the evaluation takes place. So now you can see that each one of those classes that implements expression are defined as records, which makes the entire program significantly simpler. So if, for instance, we have an expression object which is actually of the type number, the evaluation of that expression object will be very simple, because calling evaluate passing over number, it means that we get that int value the number object wraps. If the expression object that is now being evaluated is an object of the type total, as in this case, then you can see that when evaluate is invoked and it takes an object of the type total, this is the case that match, and those two expression objects are extracted and evaluated by calling evaluate one more time in order to calculate the total of those two values we get. When evaluate takes an expression which is actually an object of the type multiplication, something similar happens. The two expressions that form a multiplication object are being extracted, evaluated, and as you can see, we get a multiplication between those two evaluations. Similarly, when evaluate take an expression which is actually an object of the type difference, similar thing happens. Those two expressions that forms the difference, the object of the type difference, are extracted and are being evaluated, and then the difference between the two, this is the value evaluate returns. So everything fits. Having the type expression defined as a sealed type allows us over here to use pattern matching, covering all options in order to have one single method, evaluate method, that can take an expression of any of those types that implements expression and evaluate it. So the entire program becomes much shorter, becomes simpler to maintain. And as you can see, we could easily add new operations without modifying the type expression or any of the types that implements expressions. So if you execute this code sample, we get an evaluation of each one of these expressions, and it works fine. So what are the benefits when implementing visitor using sealed classes, records, and pattern matching? First, with sealed classes, we actually explicitly restrict which are the subclasses that can extend the interface, the expression interface in our code sample or any other interface when implementing visitor. We first start with defining the interface and then defining the classes that implement that interface directly or indirectly. And when using sealed classes, when defining that interface as a sealed type, we actually restrict the classes that extend, that can implement the expression interface, for instance. That ensure that every subclass we have, every class that implements expression in our last code sample is handled. In that switch expression, we have created inside the evaluate method in our code sample. Now, the second benefit is less boilerplate. When using records, automatically methods are defined in those records. Getters, setters, equals, hash code, and so on. That simplify the entire code, make it simpler to maintain the entire code, simpler to understand the entire code. Now, the next benefit is that we actually eliminate the double dispatch we have when implementing visitor the old way. Another benefit is an improvement in the overall performance. The virtual machine has various optimizations for switch expression. Now, the last benefit I can identify is having the entire logic in one place, explicitly expressed. That turns the entire code into something that is simpler to maintain, comparing to what we used to have before visitor was implemented using sealed classes, switch expression, pattern matching, and records. Thank you for your time and enjoy the rest of the conference.